Du coup, sur YouTube.
En fait,
Et sur YouTube, est-ce que tu me vois là?
Non.
Non.
Mais le truc, c'est que j'ai l'impression qu'on voit que l'écran de YouTube, enfin de l'écran principal qui est partagé.
Ouais, mais je sais pas comment on change ça.
Est-ce que c'est moi qui peux le faire?
C'est toi qui peux le faire.
Il y a un écho. Ah,
C'est quoi? Non, ça c'est juste YouTube. Il y a un petit délai.
ouais. Là, YouTube, view. Side by side speaker. C'est pas là? Non, je pense pas. Si je fais...
What's up, guys? Paul here from Stream Geeks, and you asked for it. How do we set up these unique tools? So, how do we set up other computers? Even Bridge have connected to MIND-INRIA.
J'ai l'impression qu'il y a un peu trop de contenu. Auto-enable YouTube live streaming for webinar, blablabla. Peut-être si Pierre-Antoine il arrive pas trop tard pour lui demander.
Vous voyez, lui?
Hein? Ah, on le voyait. Vas-y, tu peux regarder sur le.
Ouais. C'est ça. Donc là, en gros, t'as YouTube. Mais full screen, peut-être? C'est dur, mais... Ok, on va revenir sur YouTube. Non, c'est toujours bien. Comment on fait ça? Je peux enlever la vidéo dans... Attends, je crois que ça me dit un truc là. Tu sais, quand tu fais tes vidéos... Ouais, je fais ça. Ouais, Pin, peut-être? Je pense qu'on va se dire juste... ouais. Ah, attends. Et c'est là, ça, là, et quoi, la croix? Non, c'est swap share. C'est ce qu'on a fait. Choisir vidéo. C'est bien. Vous avez pas fait quoi ajuster? Ah, c'était pas là? Effet sur record. Parce que là. Bon. T'es en full screen mode, toi? Vas-y, mets pause peut-être. Change post. Ok. Ça va pas changer ça. Ok, bon, vas-y.
Hello Virginie, toi qui es super forte en live YouTube,
Oui.
tu sais comment on fait pour voir la caméra dans le live?
Le live, ça va être le zoom, donc si tu mets ta caméra, on va te voir.
On a une caméra, mais on ne voit pas.
Parce qu'en fait, moi je pense que c'est parce que c'est pas la même personne qui parle. Que t'as pas activé ta caméra.
Si, j'ai activé ma caméra et mon micro là. Il est là. Là, c'est le micro du Zoom et la caméra du Zoom. Donc, normalement, c'est la bonne. Et du coup, quand tu regardes sur le live, il n'y a pas. Non, c'est Mathieu qui a indiqué comme mute. Moi, je suis pas mute. Et j'ai lancé le live depuis l'autre, mais du coup, maintenant, je suis redevenu.
En fait, là, ce qu'on voit, c'est ça.
Toi, si tu mets ta caméra, ça marche? Si toi, tu mets ta caméra, ça marche ou pas? Et si tu regardes sur le Zoom? Ouais, c'est ça. Non, ça marche pas. Non plus.
Mais attends, là, on voit ta tête. Mais attends, donc là, vous êtes sur le zoom.
Là, en fait, là, ça, c'est le zoom. Voilà.
Ouais.
Donc, j'enlève la vidéo. Et il y a en plus, donc là, si on est
Ouais,
sur,
bah,
si
ouais.
t'es
Ouais, ça
sur
marche,
le
hein.
zoom, sur le zoom,
Non,
ça marche.
mais sur l'autre, ça marche aussi.
Si elle va sur YouTube.
Je sais pas ce qui s'est passé, mais c'est bon, ça marche.
Je suis
T'es arrivé et t'as mis les ondes magiques qui marchent.
Arrive plus souvent, s'il te plaît.
Mais ouais, quand vous voulez, hein, vous m'appelez, je débarque.
Hein?
Autant que je suis là, vous avez besoin d'être pour vous.
Bah, je pense que là, ça y est, tout est bon.
On vient de réussir à tout ça.
Ah non, il reste un
Parfait.
truc qui est passé top. C'est le son, non? Le son. Le son des questions.
Tu veux
Je
que
les entends.
Ah oui, c'est vrai, on les entend maintenant.
Ça marchait pas?
Tu veux qu'on teste?
Non, mais attends, je le teste maintenant là. Tu m'entends? Tu m'entends ou pas?
Ça marche pas.
Ça marche un peu, on refait.
Est-ce que tu m'entends?
Si, on peut.
Ah si.
Pas très fort, mais on entend.
Si.
Pas très
On m'entend.
trop fort.
C'est juste que.
En fait, c'est parce que j'ai baissé. Vas-y, parle.
J'ai peur que ce soit ce micro.
Non, toi?
Est-ce que là tu m'entends?
Ah oui, on t'entend bien.
Il y a tout qui marche.
Fantastique. Avec 30 minutes d'avance, incroyable.
Ouais.
29.
Bon, et bah super.
Tu veux que j'envoie le lien, toi, ou tu laisses pas?
Normalement, je l'ai envoyé hier soir.
Ah, le lien.
J'ai envoyé le lien YouTube, ouais.
Et donc là, c'est des gens qui arrivent sur Zoom, c'est à toi de les accepter.
Il y a personne qui arrive sur Zoom parce que du coup, il y a. Sauf les personnes qui ont le lien pour arriver. Et normalement, je n'ai pas besoin de les accepter. Enfin, peut-être j'ai pas besoin de t'accepter non plus. Donc, normalement, il y a le mot de passe et j'ai pas mis de acceptation ou pas. Donc, normalement, on est tout bon. On ne touche plus à rien du coup.
Il y a un H.
Les excuses commencent? Ah bah oui. Ça, c'est assez classique. Après, je ne peux pas vraiment en vouloir aux gens. Honnêtement. Ah, c'est faux. Non, je suis allé à celle d'Emeric je le veux, en fait, maintenant que j'y repense. Mais c'était dans mon hello! Mais c'était dans le même bâtiment que moi, donc j'avais vraiment aucune excuse.
On a juste mis 45 minutes pour le setup. Et sur l'automatique après, je pense que ouais, c'est bon, ça marche.
Mais maintenant tout marche, on entend les gens à distance nous entendent. On voit un écran, tout est sur YouTube. C'est ça. Hein? En gros, le seul truc, c'est si jamais il y a un bug, il faut. Ah, mais je vais peut-être te remettre host. Ou alors on touche plus à rien parce que ça marche. On touche plus à rien parce que ça marche. Mais je pense qu'on peut pas faire co-host, j'ai l'impression. Je peux juste faire make host, mais j'ai pas l'impression que je puisse faire co-host. Donc j'ai pas l'impression que je puisse. Si jamais, de toute façon, tu fais un signe et puis genre on fera ce qu'il faut. Bon, normalement, vu que tout est très stable. Par contre, c'est quand même pas mal le truc de genre tu appuies et il y a tout qui marche. Quand tu trouves le bon truc, quand ça marchera et que tu auras juste à plugger, là, ça va être quand même vraiment. Ok, moi, j'ai juste aller voir s'ils ont bien la liste. C'est bon, t'es soumis? Ouais. J'ai temps de rentrer chez moi. Non, c'est juste que j'ai enchaîné le midi. Dans le lit, j'ai pas mis du coup. J'ai tout l'après-midi. Je suis arrivé au bar, puis je suis posé, je suis fait, ouais, là, j'ai commencé à avoir. C'était un peu vite. Mais ça mène très vite. Ça mène. Là, on prend les métros au calme. Mais
Ouais. Félicitations. Merci. On a changé d'heure? Ouais, personne, c'est que je t'invite à me jouer. Merci. Ça va sécher. Les plus vieux, c'est
Oui, ça marche ou pas? Donc ça devrait, non.
Ça va être une team en transhumance cette semaine. Moi, j'ai mis une idée sur la. C'est vrai.
Une question que je me posais, c'est quand même comment ça marche pour les. Alors, est-ce que ça marche encore? Bonjour Patricia.
Bonjour. Salut,
Ah,
ça va?
Salut, ça va et toi?
Ah ouais, très bien.
Tu nous entends bien?
Ouais, pas de souci.
Bon, nickel. Et tu nous vois, donc parfait, ça a l'air de marcher.
Ouais.
Du coup, une question que je me posais, c'est comment on va faire pour les questions pour vous dans le. J'ai pas l'impression que ça marche.
Je suis la seule à distance du jury ou on est deux?
Non, il y a la moitié du jury à distance. Il y a deux autres. Il y a du coup David Donneau et Thomas Spock qui sont à distance, qui doivent
D'accord.
se connecter. Et du coup, après, il y a trois personnes du jury qui sont dans la salle, qui sont Julien Méral, Romain Tavenard et Édouard Oyalon.
D'accord. Ok, super.
Mais du coup, c'était ça la question, ouais, comment on fait pour interagir? Bah, la question était si on pouvait utiliser le micro, ça aurait été le plus simple. Mais c'est quoi que Alors, ça marche encore là. Alors, est-ce que ça marche plus? Ah si, ça remarche là. Ok. On ne touche plus à rien. Hello. Si on oriente le micro, Patricia, est-ce que tu entends si les membres du jury parlent?
Oui, tu m'entends là quand je parle?
Ah, on t'entend pas, Patricia.
Tu m'entends? De mon côté, ça a l'air de marcher.
Change pas speaker en tout cas. Speaker, assis speaker.
C'est ça.
Tu m'entends ou pas?
Tu nous entends encore, Patricia?
Oui, oui, mais vous m'entendez, vous?
Oui, c'est bon, on t'entend de nouveau.
Ah,
On ne
parfait.
touche plus à rien. Et du coup, si les membres du jury parlent, est-ce que tu les entends ou pas?
Non, j'entends que toi.
On n'entend que moi. Bah, je pense que du coup, on sera obligé de faire, de demander aux membres du jury de venir directement sur la scène, parce qu'on n'arrive pas à faire marcher les micros dans la salle.
D'accord.
Ça marche pas. Hein. Non, ça marche pas. Non.
J'entends un petit peu, mais je pense avec l'autre micro, en fait.
Quand je dis ça marche pas?
Ouais, j'entends faible. Mais je pense que
Ouais,
c'est parce que tu es à côté de l'autre.
oui, c'est ça, je suis juste à côté de l'autre. Je pense qu'en fait, ça marche, ça marche pas sur ce petit micro qui nous permettrait d'avoir les deux. Bon. Du coup, on fera un truc un peu plus effectivement, enfin, il faudra se lever et potentiellement, je répéterai les questions des autres membres du jury. Parce qu'on va faire on va peut-être pas faire toutes les questions directement au micro, mais juste pour l'introduction. Ok, bah du coup, il nous reste juste à attendre Thomas et David et on a encore 5-10 minutes. Parfait. Hello.
Hello.
Can you hear us well?
Yes, very good.
We can hear you too, so perfect.
Perfect.
Thanks a lot for connecting.
Yeah. Okay.
We are just waiting for David, who said he was 3 minutes late, so
Okay.
just gonna wait another couple minutes and we should be good to start with all the members of the jury, so perfect. Perfect.
Hello.
Hello.
Hello, Thomas.
Hey. Can you hear us well?
Yes.
Perfect. So I think we can hear every member of the jury too. So we managed to make all the technical work well. So perfect. We are. I think we are good to start. So I will leave the introduction. So we decided. So we need to decide of a president for the jury, and I think we proposed that it's Edouard Royalon who will act as the president of this jury. So if everyone agrees, it's gonna start with this defense. All right, perfect.
Okay, so today it's my pleasure to be the committee chair of Thomas Moreau HDR. So I'm gonna begin by introduction of the member of the committee. So first there is Professor Thomas Pock, who is at TU Graz University. Then there is Julien Méral, who is a senior researcher at INRIA Grenoble. Then Professor Romain Thévenard at University Rennes 2. Then Professor David Donneau, who is at Stanford University, who is a committee member. And then there is Patricia Reynaud-Bourret, who is a senior researcher at CNRS at University Côte d'Azur. And so I guess I will hand over to Thomas now.
All right. Thank you very much for the kind introduction. So can you see my screen well? Online? Yes. All right. Perfect. So hello, everyone. Thank you for attending this HDR defense. Thank you very much for the member of the jury who accepted to review my work. So today, what I'm going to try to do is give you some overview of the work I've been doing in the past years and try to sketch a bit the direction that I deem interested in the research for physiological signal processing with event-based models. So let me give you a little bit of context. Since the beginning of my research career, I've been working on physiological signals, which are measurement of the body functions and processes using physical sensors. So I started at the Centre Borelli, working on gait analysis and oculography, and then move on to electroencephalography when I joined the parietal team, which then became the MIND team, where we try to probe the cognitive function of the brain that is functioning. And recently, I started to be interested in more in other physiological signals, which are the signals that are used during the monitoring of general anesthesia, with some collaborators with anesthetists in Lariboisière, which is a Paris hospital. So these physiological signals are used for many different applications. I guess the one that is the most classical is the one in healthcare, trying to improve the health of patients. But you can have also other kind of in use cases for these kind of signals, which are to try to develop interface between human and computers, or to try to understand better the brain functions in the case of neuroscience. And the corresponding machine learning task that you have with these kind of signals are actually many. So the one that is once again the most classical is you say you have one physiological signal and you try to predict a single quantity for the full signal. So for instance, you have a subject and you try to predict whether this subject have a disease or not. Then you have some other kind of tasks which are more linked to the signal aspect of this data, which is what I call the sequence-to-sequence task, where you have a full signal and you're trying to construct another signal that is more informative or that you don't have access to directly. And finally, there is a third kind of task that I think is less studied in the literature, which are the event-based tasks, where what you are interested in is you take your full signal and you're interested in finding some points in this signal where you have some event or anomaly or changes, and you try to detect them or predict them. And this is what I think is really interesting in this kind of signals, and this is what I've been trying to pursue in my research. So to give an example, if we take neuroscience, and we have one subject in magnetoencephalography recording. This subject, usually you don't record him doing nothing. Most of the time you record him using some task, or you have some stimulus for this person. So here, for instance, this is a recording of a person that has some auditory and visual stimulus. And here you can see the signal that you record. So it's a complex multivariate signal that is quite noisy. And here in green, you see the event where you have the stimulus. If you look at this signal, you don't see any clear pattern or anything that is happening in this signal. But if you extract windows that are centered around these events and you average them, you can actually recover what is the brain response to the stimulus. And you actually see that there is something happening. There is some information in this signal that is actually informing you about what is the brain response to the stimulus. If we go further, so the stimulus was an external event. If we look further and we consider some electrocardiogram signals, if I ask in this audience, here there is one normal electrocardiogram and one that is not normal. Actually, I think most of you would guess that actually the normal one is the one on top and the abnormal one is the one on the bottom. And it's because actually here what you did was actually extracting some event, or what I call event here, like pattern, that represents the heart that is beating, and seeing that there is a regularity in the occurrence of these heartbeats. And I guess everybody knows that it's better to have a heart that is very regular than a very irregular heart. So here you have some latent event in your signal that inform you about what is happening actually inside the human body, and that allows you to make some decision about what is happening. And so this kind of event-based, these kind of events are actually present in many different applications for general anesthesia, where you have both this latent event that represent the different physiological events that are happening inside the body, and some external events that are happening during the general anesthesia, because usually you go under general anesthesia for a procedure, for a surgery, where you have some drug injection to induce the anesthesia, you have some surgery act, and you might want to have to detect some adverse outcomes. So the challenges in processing physiological signals are actually many. You have some challenges in machine learning. You have some challenges in signal processing. You have medical challenges because you're handling some healthcare data. And you have also some software challenges because the data is quite messy. It's recorded in clinical context. You have a lot of missing information. It's not always easy to have some very clean pipeline. My research focus mostly on few of these challenges, but that are due to the many challenges that you have. And in particular, one that I'm particularly interested in is that when you process physiological signal, you have some very high-dimensional data due to the signal nature of the data. And usually, it's very hard to acquire a lot of labels because labels are costly. Sometimes they are unclear. It's not so easy to actually come up with a right way to label these signals. And so this calls for unsupervised learning methods that are able to characterize the signals and the event distribution that we have. Unsupervised learning and self-supervised learning recently have become actually very prominent in the field of machine learning and AI, in particular with the advent of generative AI techniques that allows to probe the distribution of the signal by trying to predict some parts of a signal based on the rest of the signal. So this is the technology that is behind some very well-known tools like ChatGPT or Midjourney or Mistral. But despite the success that this kind of technique had for image and text, it has very limited successes in time series. And this is something that we have seen over and over. There are very few papers that manage to do some very good use of unsupervised learning and self-supervised learning with time series. And the reason, what I firmly believe, is the reason why it does not work for now with physiological signal is the fact that actually the information of interest in this kind of signal is actually sparse. It's not as dense as in an image where you have a lot of information or text where each token is actually informative about what is happening, but it's actually localized around some events. And so the vision that I have on how we should process this kind of physiological signals is the following: is instead of trying to replicate what is done with images where you have some observed signal and you try to directly predict the remaining part of the signal. So here, using some forward prediction of what is going to happen in the signal, what I think we should do is try to take the signal, then do some unsupervised event detection to discretize the signal as some tokens that are the latent event, increase them with the external event, and then have some discrete event model that allows you to actually generate what is going to happen next in terms of events, and then go back to the signal. And I think this is what is easier to do, and it allows to select the information in the signal instead of trying to reproduce all the signal with all the noise and the lack of information, or maybe there is something that there is nothing actually in the signal. Because most of the signals, sometimes nothing happens. So to reach this goal, I've asked myself many different questions. I'm not there yet. I think it's not working for now. We only have some proof of concept, and I asked myself various research questions. The first one is about how to do unsupervised event detection in the signals. And for this, I actually worked a lot with a technique called the convolutional dictionary learning, and I've been trying to scale and adapt it to the physiological signals, in particular, trying to use some unrolled architecture. And the first part of my talk, we explain a bit what was the journey on trying to scale this technique for the physiological signal. The second research direction that I've been involved in was how to actually come up with models for the events that are adapted for the physiological events, and in particular that are able to account for delayed interaction between the events. And this will constitute the second part of my talk. And the third research direction that I've been following is also, okay, if we have a new model that is based on the event, how do we evaluate this model? How do we make this reproducible, and how do we make this evaluation reproducible and sound? And I will also present some of my work in this direction. I've been also asking myself other questions around data augmentation, bi-level optimization that I won't touch during this presentation, but which are still linked with the work that I present. So without further ado, I will start with the first part of my talk, about how to try to accelerate convolutional dictionary learning based on algorithm unrolling and bi-level optimization. So this is work that started as a collaboration with Pierre Ablin and Gabriel Perret, and that we continued with Benoît Malézieux, my PhD student, that we had with Mathieu Kowalski. And so actually, let me explain what is the convolutional dictionary learning, which was introduced by Gross et al. in 2007. And so the key idea of this is to try to get a signal and find the recurrent pattern and their localization in time. So here you have a signal X that is clearly composed of 3 patterns that are repeated, that are very similar. And what you want to do with this convolutional dictionary learning technique is to decompose this signal as a pattern that is the local shape that is repeated in the signal, and the localization in time, the localization that this pattern has in time in the signal. So which is represented by this vector Z, which is actually sparse activation vector that is telling you where the pattern is localized in time. So in mathematical terms, this means that you want to decompose your signal X as the product of convolution between a pattern D, which is the atom, which is basically the recurrent pattern that you want to find, and Z, a sparse activation vector that informs you about the localization. So to be able to infer both the localization and the pattern, you can come up with an optimization model, an optimization program that looks like this one, which is a min-min problem, where you have first a data fitting term that is this term that is measuring how well you reconstruct your signal X based on this product of convolution, plus some regularization term that enforces the fact that you want Z to be a sparse activation vector. So it's just a constraint that you want to do. And so this problem can actually be solved quite easily, not so easily, but with a simple technique, which is called alternate minimization, where you come up with some patterns D that you fix, and you compute what is the localization of this pattern D, and then you solve the reverse problem. Given this localization, what are the best patterns to reconstruct your signal? And you can alternate between the two. The thing is, actually, you can also see this problem as a bi-level optimization problem, where you have this kind of thing where you want to find D such that you best reconstruct your signal, given the solution of another optimization problem that is finding the best possible localization for any D. The nice thing about this bi-level formulation is that now you have only one variable you want to optimize on. And so the question that we ask ourselves is, can we actually accelerate the resolution of this convolutional dictionary learning based on this bi-level formulation? Because both formulations are actually exactly equivalent. And the thing that we think, why we thought we could actually accelerate, we could actually accelerate the resolution of CDL based on this compared to alternate minimization is that because alternate minimization does not account from the fact that Z star will change when D move. So maybe taking this into account will allow to accelerate. So if we look at this bi-level formulation and we want to be able to solve it using optimization, what we need to be able is to compute the gradient of our function h of D, which is the function that we want to minimize, which is the outer function of the bi-level problem. And so we have something that is very convenient. There is a theorem by Danskin in 1967 that tells you that actually the gradient of this function is actually very simple. It's just the gradient of the function where you consider that Z is fixed. So it's exactly what we do on alternate minimization. And actually the approximation that we do in alternate minimization and why we don't have really the real gradient is the fact that instead of computing this quantity in Z star, we compute it in Zn, which is an approximation of this optimization problem solution with n step of a given algorithm. The idea of unrolling is to say, okay, maybe we can take into account the fact that when we move D, actually Zn will also move, and this can give us some benefits. So if we consider the unrolled formulation, we replace here Z star by Zn, which is an approximation with n step of an algorithm. And then the gradient estimate, if you compute the gradient estimate, it becomes something like this, where the first term is the same term as the gradient in the alternate minimization term, plus you have a correction that takes into account the fact that Zn will move when D is moving. And the convenient thing with unrolling is that it's super easy to compute because you can just use backpropagation through the algorithm, and this gives you the true Jacobian. I will just mention that there is a third approach that you can take, using implicit differentiation. You can have another formula that is based on the Jacobian if you consider that Zn would be the exact solution of your original problem. But I won't enter into the details for this one. And so the question that we can ask is which approach is the most equivalent, is the most efficient to approximate the gradient, G star. So with these three estimates, what we were able to, we studied them with Pierre Ablin and Gabriel Perret, and what we were able to show is that actually the alternate minimization approach, the estimate of the gradient is actually converging as fast as the estimate of the solution that you have for the inner problem. For the unrolled approach, this is something that is going faster. This is going faster, so it's a small o of this convergence rate. And for the implicit approach, you have something that is going twice as fast because you have a squared term here. And so if we try in practice on small problems, on small quadratic problem, we can see exactly this thing happening where you have this order between the three methods. And you can see here in dark, the convergence rate of Z, and you see that it's the same for G1, but faster for the other two. So the proof for this is actually quite simple for the alternate minimization, because the alternate minimization, you can show that you converge as fast as the n simply based on the smoothness of the gradient of the function f. So for the second part, for the unrolling part, it's a little bit more complex because you need to account for the Jacobian. And if you look at what is happening using some kind of Taylor expansion, you come up with this kind of inequality, where you see that you have a quadratic term here, so we are going faster than the n, plus you have a term that is going in Zn minus Z star times how well the Jacobian is approximating the true Jacobian. So to be able to say anything, we need to study how well the Jacobian n is approximating the true Jacobian at the solution. So the issue here is that we need to specify with unrolling, to be able to study anything, we need to specify which algorithm we are considering. So here, if we consider the gradient descent algorithm, actually you can show pretty easily that the Jacobian verifies this kind of recursion formula. And under some smoothness condition, if Zn converges toward Z star, then the Jacobian estimate converges quasi-linearly toward G star. And so this means that you have something hence you get the result. That we showed, that the unrolled algorithm allows you to get an estimate of the gradient that is better. That is better in this case. But if we come back to so all these results that maybe I forgot to mention, but all these results only hold for a function f that is strongly convex and smooth in Z. And so what about the original problem? And the original problem was, can we actually accelerate the convolutional dictionary learning and for this? And actually, the convolutional dictionary learning is a problem that is non-smooth because of the L1 norm, the L1 regularization. So in this case, the approximation algorithm for Zn is actually the proximal gradient descent E star. And what can we say about this? And so we get some similar equations. But this is what we studied with Benoît Malézieux and Mathieu Kowalski. And when we studied the way the Jacobian the Jacobian that we estimated with E star was going to the true Jacobian that we wanted to estimate, we got this relationship where you have an inequality that is showing that is composed in two terms. The first term is a nice term, nicely behaved term, because this term actually converges linearly towards zero as n grows to infinity. So it means that the more iteration that you do, the smaller it gets, so we would get some acceleration. But there is a second term, an error term, which may actually increase with large n, but start to vanish as soon as the ISTA algorithm reaches the support of the true solution that we are trying to get. So this means that once we are on the support, the Jacobian converges linearly toward the true Jacobian, and we recover some fast rate of estimation, or some faster rate of estimation for unrolling compared to alternate minimization. But before reaching the support, this error term can actually accumulate, and we showed some matching lower bound that show that actually there is always some cases where you will have this kind of blow up. So it is to note that BN can actually be attenuated using some truncated backpropagation. And so we ask ourselves, okay, this is only some upper bound. Is this happening in real life? And so we went for empirical evaluation.
May I ask a quick question?
Yes.
Will you explain the notion of once the support is reached?
So should we keep the question for?
You can do it later. I mean, it's just that it's
if it's okay with you,
it's involved in the
we can.
statements of your results, so it needs to be explained at some point.
Yeah, I can explain it, and I can explain it now if you want. So here, if you solve this lasso problem, so this problem here with a sparse solution, then the solution will have a lot of zeros and a few non-negative coefficients. And what we call the support of the solution is the coefficients that are non-negative at the argmin of this thing. So this means that the support of the solution is the coefficient that are non-zero in this Z star of D. Does that answer the?
Right. I understand. I understand what you mean by the support of the solution, but when you say once the support is reached, so I imagine that you've got an iterative algorithm.
Yes. So the
you have
proximal
implicitly some polyhedral.
Yes. So we are using an ISTA algorithm that is a proximal gradient descent algorithm that is an iterative algorithm, and when you increase the number of iteration n, you will refine your iterate, and at some point it will converge to the true solution, or at least to one solution if it's non-unique, or the true solution if there is only one. But before that, it can reach the support of the solution before, and then at this point you have some convergence. You have some better estimation for the Jacobian.
Okay, so it just to be clear, so if I were using interior point methods to solve certain things, I would never be on the support. But you're saying that this family of algorithms, in contrast,
this family of algorithms, there are some results showing that the support is reached in a finite number of iterations. Yes.
Okay, thanks.
You're welcome. All right. So for the empirical evaluation, so we did some empirical evaluation in some typical case where when we generated some random Gaussian dictionary and tried to see how well we estimated the Jacobian on this problem. And so in blue you see the distance between the true support, so the S star, and the estimated support with the ISTA algorithm. And you see that as we increase the number of iterations, we refine the support, and at some point we reach the true support. There is a zero distance. And in purple red, you have the distance between the Jacobian that is estimated using unrolling and the true Jacobian. And here you see that once we reach the support, actually you have a linear convergence of the Jacobian toward the true Jacobian in both cases. But before this, you have kind of two regimes. This is something that is stochastic, so that depend on what is the point you are evaluating this to. But here, depending on the number of iteration, here you see that you can actually have an explosion of the error of the estimation of the Jacobian when the t is increasing. So this means that the estimation of the Jacobian using unrolling for the ISTA algorithm might actually be unstable and lead to bad won't provide some benefits for solving the convolutional dictionary learning problem. So there is something
on your plot, I'm sorry, we're supposed to infer that when the blue curve is hitting 0, that's when the support is reached. Do you know the
yes,
moment?
exactly.
Yeah.
This is the L0 distance between the support that is estimated at iteration t and the support at the solution.
Thank you.
And so once it's reached 0, then it means that we reach the true support. And so the nice thing about this result is that it also showed that actually it's possible to actually attenuate this effect by using some truncated backpropagation. So meaning that you stop you start to compute your forward pass, and then you compute the backpropagation only through the last let's say n layers of your n iteration of your algorithm. And this allows to reduce the number of errors that you accumulate with this bn term that we showed, and this avoids a bit the explosion. The issue with truncated backpropagation is that once you reach the iteration, when you reach the true support, you have some kind of lower precision result because you don't actually compute a full backpropagation, so the real Jacobian that you wanted to compute. So to wrap up on this topic, actually on the fact that trying to use unrolling to accelerate the resolution of convolutional dictionary learning, actually what we obtained with this result was the fact that we did not get the expected performance boost in the non-smooth case, and in particular in the convolutional dictionary learning, because actually the Jacobian estimate is stable only for a very low number of iterations, or at least you can ensure that it's stable only for a very low number of iterations. So what does this mean for unrolling and for the benefit of using unrolling? And so the thing is, unrolling is still something that is very convenient, because this means that instead of taking an optimization program and having to solve it at each iteration to be able to solve to compute the solution of your optimization problem, you can replace this with an iterative algorithm that you iterate and where you iterate n step of an iterative algorithm. But the thing that you need to be careful is that when you consider some non-smooth problem, actually this cannot be interpreted as solving exactly the problem where you have this z star, so the real solution of your problem. And this is actually something that is often put into as a benefit of unrolling, is that it's very interpretable, because you can interpret the unrolled algorithm as the solution of this real thing. And I think it's something that we need to be careful when we say, in particular, because this result, when you are shows that if you're using some non-smooth optimization, then actually you're not really independent on the way you have obtained your unrolled your solution. Basically, depending on the algorithm that you use, you might have something that is different. And this is something that we showed in collaboration with Zachary Ramsey, Pierre Ablin, and Gabriel Perret. The fact that you have some, you might have some mismatch between the solution if you change your procedure at test time compared to how you learn your model, if you change the algorithm you use to obtain the n. Another thing that is quite bothersome with this unrolling thing, and the fact that it does not converge, is that it's not always compatible with warm starting, which is kind of the cornerstone that is necessary to make bi-level optimization algorithm converge, as we have shown in many different work, in particular the work by Julien and Thomas, but also the work we did with Mathieu Dagréou and colleagues and Benoît Malézieux. All right, so I will now move on to the second part of this talk about how to model event distribution with point processes. So this is a line of work that started with the PhD of Cédric Alain, and that we later continue with Guillaume Sterman as a postdoc and Virginie Loison as a PhD, and in collaboration with Alexandre Grandfort. So the thing is, so we have seen that there is some ways to go from empirical data to events, for instance, using convolutional dictionary learning, but you can also use some traditional event detection techniques that convert the signal into a stream of events. And the question is, how do you characterize this event in time and the distribution of this event in time to be able to say anything about these events? So to do this, you can try to model the distribution of event in time using a convenient tool that is the point processes, which is something that is actually used to model the distribution of events in a domain, and temporal point processes that are adapted to time function. And these temporal point processes are usually characterized by their intensity function, which corresponds to the rate at which event appears. So you can see this, the lambda t, as being the probability of observing an event at time t. So the inference means that you want to try to infer the intensity function. And so a convenient tool, a convenient process for this, because there are many different point processes, and a convenient model to try to capture the interaction between different models are the Hawkes processes that were introduced in 1961 by Hawkes. That represents this intensity function as the sum of some external event happening inside your stream of event, plus some interaction terms that are the sum of different the sum of different components of different interaction between all the past events, and that will change the intensity at time t. And here, the kappa theta is a kernel that actually models the interaction between the events. And so the nice thing about this is that you can go from the event to a characterization of this event, saying, okay, after one event, here is what all these changes in the probability to observe another event later on. So to be able to do some inference with Hawkes processes, so we did a lot of work with Cédric Alain and Guillaume Sterman to try to come up with novel ways of inferring processes in the case where we want to have some kernels that look like this, that model some delayed interaction between the events that are parametric kernels that models these delayed interactions. So
is there I'm sorry to keep asking questions, but is there a constraint of the kernel kappa causality or minimum phase, minimum delay, in anything about the kernel?
The kernel need to be have a support. So we are only using kernels that are causal, in sense that it's zero. It's negative. The support of the kernel is only in the positives. So yes, there need to be, but there is no assumption of minimum delays, and in particular, most of the time, what is used are exponential decay kernels that start at some given value and just exponentially decrease.
Okay, and you'll explain the parameter theta to us.
So I choose to not explain too much, but this is this kernel are parametric kernels, and so theta is just the parameter of the kernel. I won't go into the detail, but usually what we use are kernels that are raised cosine kernels that have some phase, some delay for the kernel, and some width for the kernel.
Thank you.
So just simple parameters that allows to capture some information about the event distribution. All right. So to do the inference with Hawkes processes, usually what you try to come up is with an optimization program trying to either minimize the negative log likelihood or the L2 loss. And in both cases, you obtain something that looks like this, where you have two terms. You have a first term that is actually an integral term that is trying to regularize how high the intensity is on the full segment that you're observing when there is actually no event, plus a second term that is trying to minimize to maximize the intensity at the location where you have some event TK. And so here, phi and psi are simple functions that allows to balance between a negative log likelihood or L2. And here, actually, the computational bottleneck to be able to do the inference is actually to be able to evaluate the intensity function at the different time tk, because you need them in this sum. And usually, this term is actually a term that is fairly simple that you can compute in closed form based on the parameters. And most of the time, the choice of the kernel is driven by this computational bottleneck, because there is one type of kernel for which this is efficient, which are the Markovian kernels. So typically, this is the kernels that are obtained with exponential kernel, where it's actually easy to compute the intensity function lambda t at time t plus delta t from the value of the intensity function at time lambda t for any theta. And this means that using this property, you have some efficient procedure that allows to compute the intensity at time tk in linear time in the number of events tk, which is fairly efficient. The issue is that if you want to move past exponential kernel and you want to be able to use general kernels, naive computations of lambda of the intensity function at time tk are quadratic in the number of events in the number of events that you observe. And so what we proposed with Cédric and Guillaume was an inference procedure called FADIN, where we only consider the L2 loss and we use some discretization of the time. And using this, the nice thing is that we can actually rewrite the inference loss as a program that looks like this, where actually Z is a sparse activation vector that is equal to 1 if T is associated with an event TK and 0 otherwise. And here, the nice thing is that this loss is actually very similar to the loss that we are optimizing in the convolutional dictionary learning setting with the dictionary updates, because here, if we want to update kappa theta, then this means this looks very much alike as when we were optimizing for the atoms in the convolutional dictionary learning technique. And so this loss can be actually minimized efficiently when the kernel has a finite support using some pre-computations. So really FADIN, the idea of FADIN is the ingredient of FADIN are three. The fact that we use the L2 loss, some discretized time, and some pre-computation to make the inference very efficient. So FADIN allows to use some finite support kernels. So we did some with this method that I want to present in more details. We were able to show with empirical evaluation that the bias due to the discretization is actually going to 0 as the discretization is refined, and so reaching some errors that is equivalent to the statistical error that we do because we observe only a finite realization of the process, and so which is not due to the discretization. And we are also able to show that the optimization complexity of this procedure is actually independent of the number of events that we have. So even if we increase t, meaning that we increase implicitly the number of events that we are seeing, the inference procedure time, aiming is not too large. So if we go back to the original setting where we want to characterize the response of the brain to stimuli, using some convolutional dictionary learning and this kind of and fadin. What we are able to do is using convolutional dictionary learning, we are able to learn some patterns from these multivariate signals. And the pattern that we recover are atoms that looks like this. So it's multivariate atoms. We impose some extra constraint to make them look like plausible brain activations. And so this is something that we are able to recover with unsupervised event detection from the signal. And the nice thing is that using also the methodology of event-based of event modeling and modeling what is the intensity, what is the influence of the stimulus that we obtain on the activation of these atoms in time, we are able to recover this kind of graphs where here at 0 we consider that we have the stimulus and we look at the change of the intensity function, so at the probability to observe the activation of each atom as the time goes. For the stimulus in blue, that is the auditory stimulus, and in orange, that is the visual stimulus. And the nice thing here is that here we have a large spike around 100 milliseconds after the stimulus for the auditory stimulus, showing that these atoms that we learn in an unsupervised way from the signal is actually an atom that corresponds to the response of the brain to the auditory stimulus. And we have something that is very similar here for the visual stimulus that is showing that this response is actually the evoked response for the visual stimulus. The nice thing compared to the previous analysis is that we gain something more here because here we are only able to see the shape of the response to the stimulus, while here we are able to gain the shape of the response to the stimulus, but also the delay and the variability in the delay for a given subject. So this is something that allows to probe some interesting information about the brain. Let me mention very quickly that most of the time when you use empirical data and you use some event detection, you end up with very noisy event detection. You have a lot of various noise, and in particular, if you're using convolutional dictionary learning. And in this case, it's actually very hard to actually do some inference for this kind of event stream. And the nice thing and that we proposed with Virginie and Guillaume in a recent paper was to try to come up with a way to automatically classify the event between the ones that are structured, that are the ones that usually we are trying to look for. So for instance, here in an ECG signal, you know that you have roughly one activation, you have one heartbeat every second, and that all these small activations should be noise. And what we propose with an app was to try to classify the events that we obtain based on their temporal distribution and based on the structure that you have between the different events and based on the fact that you have some spurious event in the middle. So in this work, we derive some mixture of various conditions for various cardiac conditions for patients. And so using automatically just the convolutional dictionary learning and an app, we were able to recover some estimate of the heart rate variability and of the delay between the different heartbeats in the signal. And the nice thing about this is that we were able to, with a method that is not designed explicitly for this, we were able to recover some performances that are comparable to the performances of dedicated software that are dedicated to estimating this kind of things. So showing that this is an unsupervised method that allows to detect some events and to characterize their distribution and provide some interesting information for the doctors to work on. All right. I will now move to the last part of my talk about reproducible method comparison with bench-opt. So this work is a work that started as a discussion with Alex Grandfort, Joseph Salmon, Mathurin Mathias during a NeurIPS conference where we were very angry at the fact that there was not enough reproducible conference and everyone was kind of cherry-picking the method that they were comparing together. So we started a library to try to robustify and to make method comparison more reproducible and shareable between the different labs. And we are later on joined by many others on this journey. And so to maybe to give the context, I think that benchmark are what fueled a lot AI progress. In particular, if you think about ImageNet, this is something that give rise a bit to the deep learning trend and show that deep learning was really something that might be worth investing a lot of research in. But actually, many fields lack a reproducible reference benchmark. And we see a lot of different papers saying, do we really need foundation model for forecasting? Like what are we doing in this field? Because there is something that is probably wrong. And most of the time, this is because the evaluation is flawed because we don't have a reference benchmark. And so with this, we see that many new methods are published, but it's not always clear that there is an improvement in the literature. So a typical case for this is the deep learning optimization literature. And recently in 2021, there was a paper listed more than 122 optimizers designed for deep learning optimization. They tried a lot of them, and they said, okay, there is no clear winner that is actually beating often the Adam optimizer with default parameters. So this benchmark was really interesting because it was showing, okay, maybe we need some better way to evaluate the progress. But also, this benchmark is not actually easily reproducible because it's hard actually to run. And so the idea that we propose with bench-opt is to try to take a community approach, trying to provide some nice tools and some nice way to share and run the benchmark and to organize the benchmark in a way that is easy to extend and use by others. So this is something where a lot of people contributed to create some example of benchmarks that could become reference benchmark in various fields. So we started first on doing some optimization benchmark to try to robustify the comparison in the optimization field, but we also move on to more general machine learning models like unsupervised domain methods like unsupervised domain adaptation or brain-computer interfaces, trying to improve the way we compare things. So maybe let me just give you an example of why and what we did with this library. And so we considered, for instance, the idea of doing some optimization for ResNet for image classification, which is a task that is done in almost any lab that is doing machine learning and computer vision. And so there are various optimization strategies. But actually, we started this work because we realized that most of the time, this is the baseline that you need to evaluate your work, but it's actually very hard to reach state of the art. There are many tricks that are involved that make it possible to reach the performance that is reported in different papers. And so what we tried to do in particular with the work of Zachary Ramsey was to provide a reproducible optimization procedure to reach the state of the art using both PyTorch and TensorFlow that allows to reach the best possible performances. And this benchmark was published and is now used in many papers as the reference that is something that is rerunnable and that we can actually improve in time. So the roadmap that we are trying to take with this library is actually to try to develop new reference benchmarks in different fields to show that actually this library is versatile enough and the benchmark can be maintained in the long run. In particular, with a lot of collaboration with diverse team and diverse fields. So, for instance, with the SCADA bench on the domain adaptation, with Eric Flammary, Théo Nationou, Antoine Collat, and others, but also for BCI or time series anomaly detection. Another thing that we are very interested in with BenchOpt is to try to also improve the benchmarking methodology to make sure that these benchmarks are actually producing valid conclusions. And in particular, answering the question, how to ensure that a method is better than another. So we are investigating the confidence in ranking depending on the number of samples, the number of cross-validation strategies that we use. And we hope to provide some good guidelines to make the benchmark more reproducible with this. So with this, I'm reaching the end of this presentation. I would like to thank all the collaborators that I've been working on recently. I could not fit everyone on this slide, but I mean, I would not be able to do all this work with all these peoples. And I would like to conclude to say that, yeah, if you try to place Thomas Moreau in the various field and the various work, I think what I try to be is trying to provide some new methodology for machine learning that is applicable to physiological signals and that will have some impact with my work, with my collaborations with anesthetists. And all this is supported by a strong foundation in open source that I think is fueling the progress in this field. Thank you very much for your attention.
Okay. So thank you, Thomas, for your presentation. So it's going to be like the question session. So to remind, first, we're going to start with the reviewers of the manuscript. And then we will go through the other members of the committee. And so for now, I do propose to begin with Professor Thomas Bock, if you can hear me.
Okay, can you hear me?
Yeah.
Thomas, thank you very much for your very nice presentation. Most things, I think, were very clear. I was wondering in the very beginning, you said there are unclear labels. So which means that the ground truth is unclear in some sense, right? So
yes, exactly.
Evaluate your methods. I mean, without labels, you will never be able to evaluate it.
So yes, that's true. So actually, it's unclear labels because we are working with medical doctors that often it's very hard to come up with a nice way to frame the problem. So often they are interested in various effects that they observe in the signal. Most of the time they are really expert of the signal and they know how to. They are able to tell you, okay, with this signal, it's this kind of thing is going to happen. But this is a varying target. This is a moving target because often they tell you that there is something that is very important that you need to be able to predict, but actually they are not able to define it very explicitly. So this is why I think we need to, or some way to summarize the signal in a way that is that the doctors can work on and actually clarify the label in the end.
Mm-hmm.
So I don't know.
I know this problem very well, so therefore I was asking what is your take on that. So when you talk to people in medicine, they try to find something, but they're not sure what they want to find.
Yeah, exactly. This is what I meant with unclear labels, because it's true that sometimes they tell you, yeah, but this is what is really important, but in the end, it's not really this. And so this is why I think, and sometimes also these results, often this is unclear labels, so they know what is the clear label at the end. They want to improve the patient care. But they often, the intermediate step where they say, okay, if we are able to get this, we will be able to improve this. This is the unclear label often. And so this is, I think, why we need some good way to summarize, to be able to evaluate the link between what they really want to be able to predict, and so which is like improvement in patient care and the signal.
Okay. Second question. So you mentioned that there is so far limited success of generative methods for time series. Why is this the case?
So there is multiple answers. First, I think maybe it's a broad statement. There are some successes. For instance, this paper by Banville et al. Is actually one success story in this field of using unsupervised learning to come up with a nice representation that are quite interesting to understand the signal. But the thing is, I think most of the time when you look at foundation models for time series, they try to be holistic for all type of time series, for all type of tasks. And most of the time, I think they fail. And we have seen many different papers saying, okay, actually this foundation model is beaten by a simple AR model. And I mean, this was, for instance, in ICML last year, we saw some paper proposing some kind of AR model with 1,000 parameters that was beating all the existing foundation models and fancy transformers. And I think the reason why is because we don't have good benchmark to evaluate the progress on this field. And also maybe people are trying to do some too broad tasks where you don't have enough, I mean, text in a sense is kind of, it's quite restricted. You have only like 60,000 words per language. Even though you have many language, you have something that is quite coherent between the different language. You have some similarities, and you're able to work with all the text in the world. It's gonna work images. It's kind of the same. While for signals, I think the signals are much more varied actually. And so I think you would need a much larger number of signals to be able to learn the foundation models that is able to tackle all the possible signals. And so I think like specialized foundation models for different types. So for instance, for physiological signal, I would believe it more, but for now, I haven't seen some that are completely convincing at least.
So I was wondering, since you're dealing with real world signals, you have noise, you have uncertainties, you have wrong labels. I haven't seen Bayesian approaches. You could also, you know, make this thing all more Bayesian. What is your take on that?
So hard take. No, but for the uncertainty, I mean, yeah, I would say the take is most of the time I find that when you use Bayesian approach, you start increasing a lot the computational budget, and it's not always the benefit is not always super clear in the end about the uncertainty, because the uncertainty is usually a good estimate of the uncertainty as long as your prior don't have too much mismatch with the real priors. And most of the time, your prior is quite. It's hard to be sure that it's the right one. So it's not. I mean, it's not a completely ideological take that I would not use Bayesian method. I think in some problems where you have low dimension things that you want to estimate, Bayesian methods work pretty well. But in high dimension, sometimes I don't see that much benefit in my opinion.
Okay. Maybe a more technical question. So when I go to the dictionary learning, you first mentioned alternating minimization. Did you ever try alternating linearization, like Palm? So where you just make one step on the one variable block of variables and then the other step.
Yes. So actually, when I mentioned alternate minimization, it's kind of like a very broad step of methods. Most of the time, you don't go to convergence for each of these methods, and sometimes you can even take only one step. So we explored various approaches. I find that usually, if you are ready to, in my experience, alternate minimization works as well as Palm-like technique. I mean, it's kind of similar in terms of performance. In particular, if you have some efficient ways to regress this Z. So usually we are using some coordinate descent that are giving some quite fast estimates. So I don't see clear benefit, but I don't see clear benefit between the two, basically. And so I'm more used to doing mainly alternate minimization techniques.
I have very good experience with inertial methods or Nesterov-like methods, alternating linearization. So I think they are hard to beat on this kind of problems of what I tried so far on my own.
So
but maybe let me ask something different.
Maybe we did a better benchmark to compare them then.
Yes. When you showed the bi-level objective, so I was wondering, is the solution the same as the original problem? No, I guess not, right?
So
the solution for D and Z as the original dictionary learning problem do they share the same set of minimizers or stationary points, I have to say?
Yes, I think so. Because you're minimizing relative to both. So they share the same stationary point.
Okay.
The stationary point for one is a stationary point for the other. But as it's a non-convex problem, you won't get the same solution if you run both.
Sure. What would happen if you would change the loss of the upper level problem? You could minimize the L1 norm or some Huber norm, whatever. Then I guess it's different, right? So you have more freedom here, right? In the end.
That's exactly right. And for instance, you had some work. There was some work before trying to also come up with task-driven, for instance, dictionary learning, where you try to add some task twists, let's say, to this thing on the upper level. The work by Julien, and I think this formulation allows you exactly a lot more freedom because you can incorporate some extra terms. Yes.
So actually, I don't know how much time I do have, so maybe I should stop at some point and let the others ask questions.
You have as much time as you want, but
really? So maybe then let's one additional question. So you mentioned when you do unrolling, you're not free in how you reach xn, right? So is this also related to the initialization? I guess, I mean, you could initialize the unrolling with the solution, right? What do you get then? Does the method break down then, or what happens?
So yes, you basically this is exactly right. The thing is, when you're using unrolling, most of the time you're fixing the initialization to some given value. And this is actually changing the dynamic of the optimization problem. So changing this initialization will actually change the dynamic and change the optimal points. But if you initialize to the solution, then I guess you have something in this particular case where you have a min-min problem. If you initialize with the solution, then you will have actually in the inner problem you won't move at all, and then you will have something where you have this gradient actually. Because this is the nice thing, the fact that actually the gradient, the KKT condition, make sure that actually the derivative in Z star is actually 0. So I mean, if you are able to initialize with the right solution, then it becomes not really it's a simple single level problem basically because you can compute the true gradient.
Yeah. Okay. I see. Thank you. I think I'm done and let the others ask questions. Thank you.
Thanks a lot.
Okay, so now we're gonna go through the other reviewers. I guess because they're on site, maybe Thomas, you could repeat the question. That could make sense.
Okay.
And I guess we'll start with Julien.
Okay. Thank you for your presentation and for inviting me to review your manuscript. Okay, first question about bilateral optimization. So we can think of many use cases where the inner problem is non-convex. Are there many success of bilateral optimization where the inner problem is strongly convex? Or what is your basic opinion so far about the success of bilateral optimization and what remains to be done?
So the question is, in bilevel optimization, here we are assuming that the inner problem is strongly convex, but often there are many use cases where it's non-convex actually. And what is the state of the field in this case of non-convex, and is there any good use in the strongly convex case? So first, I think that many of the work that consider bilevel optimization consider the work from a very theoretical point of view. And so for the theory, it makes the life much easier to consider the inner problem as a strongly convex objective because you have a unique solution, so everything is well defined. As soon as you're non-convex, then you need to handle the fact that you have a different you have multiple solutions, and it becomes much harder to work with. So I think the strong convexity, I haven't seen any clear application where you win where you have some strongly convex objective in the middle, and so I think it's mostly a theoretical object. That being said, I think I have seen some work, in particular the work from Pierre Ablin, who work a lot with bilevel optimization in the context of fine-tuning LLMs or doing some mixture of experts for LLMs. And in this case, even though the inner objective is not strongly convex, in practice they get some pretty good performances. So I think there are some ways to make the bilevel optimization work, even though the inner objective is non-convex. But this is a mismatch with the theory. It's not clear why yet, and often also you're not using the exact same algorithm. You're using some ADAM in between, which are stabilizing actually the estimation. So I think there is still a lot of work to match the theory with the practice in this field.
Then just a quick clarification when you had a slide with the convergence of the Jacobian. Just to clarify about the results, when you have a convergence of the Jacobian, it was Gn or something. Is it in operator norm that you have a convergence? Or what was the nature exactly of the convergence? So when you say convergence scarcely linearly, what does it mean?
It was the convergence in operator norm, yes. Oh yeah. So the question was for this convergence, what was the nature of the convergence? Was it a convergence on operator norm or any other? So yes, it was a convergence in operator norm, and here this is simply because you have some kind of contractant recursion. As soon as rho is small enough, you have something that is contracting and that is actually converging to the inverse of this matrix times this one. So actually, it's some kind of solution of the resolution of a linear system in this case that is going quite fast. And so it was the convergence in the operator norm for this one.
And so it was not something as, I mean, it was something even, did you have a rate, not a asymptotic rate, or which is
Yes, we have a non-asymptotic rate for this So I put quasi-linearly because we have the rate in the paper. I did not want it to go into too much details for this. And also in this paper in this paper we show the rates for other algorithm like the stochastic gradient descent algorithm, or also in some yes, the stochastic the gradient descent algorithm, showing that you had some similar performances. Similar gain, like super, what we call the super efficiency of the unrolling in this case.
Okay, so then maybe moving to the part on the convolution, I mean on physiological signals. I have a question which is a bit long and not super clear, so it's hard to repeat. Be prepared. So I think to analyze this time series, the basic convolutional dictionary learning formulation has already the first issue, which is that the representation of the events is represented as a sparse vector. But that means that if you are, let's say you have the right dictionary, if you have almost the right solution, but you are missed by one small time unit, you get a solution which is very far from the true solution. You get an iterate which is very far from the true solution. And so that means that the prime is very badly conditioned. As soon as you have a bit of smoothness in the atoms of the dictionary, basically time correlation. And so it suggests that the right representation should maybe not be a sparse vector, but a set of continuous time points. So it kind of motivates as well what you did later with the box process. But so from what I understand, what you did in your work was to first learn the atoms using a CDL and then do the better modelization of time with the box process. But could you do something which is joint, where you post first you model your time events as continuous variables, such that if you are, let's say, at time 0.5, then if the solution is 0.5 and you estimate 0.51, it's considered to be good and not orthogonal to the solution. Have you thought about all of this?
Yes, so I will try to repeat the question. So here in convolutional dictionary learning, one issue with the sparse vector representation is the fact that if you have a small shift of 1, then you're as far to the solution as you have. You're very far away from the solution. And the thing with the second part, trying to use some intensity, some smoothing of this, makes it possible to kind of smooth a bit this representation, because you convolve it with some kernels that make it easier to compare. And so the question was, is there some way to do, and here we do it, first we learn the atoms, then we model the distribution of these atoms. Can we do it jointly? And what can we say about, is the sparse activation vector the right representation? So there is two answers to this question. The first one is the fact that actually for this kind of signals, as we are interested in the timing between the events, we don't really care that much of the fact that you have a one delay in your sparse activation, because a one delay is just like a one sample delay in your activation. So this means that for the temporal distribution, this does not matter that much. And actually, so one of the comments was the fact that convolutional dictionary learning is actually badly conditioned, because you have some correlation between the atoms. But the solution that you recover is not actually badly conditioned. The solution that you recover, if you shift everything by one, is actually not so far from the true signal that you represented. So this sparse vector is actually also some nice representation of this in terms of the distribution in time. So I think that this issue about being badly conditioned is maybe not so much an issue. It's an issue for optimization and for convergence and for classical distances, but it's not so much an issue when you use actually this representation. And for the second part of the question, would it make sense to try to come up with a way to do both the temporal modelization and learning the atoms together? I think this is really like the direction I want to go in, because this makes a lot of sense, and actually it would help a lot the dictionary learning also to say, okay, here you're looking, you're trying to put some activation, but actually there is very low probability to see anything. So if the activation is not high enough, you should not put it. And so this would also help solve a bit this ill-conditionedness issue, let's say.
Okay, so maybe a last question. So we are touching also maybe the limitations, the future directions. So are there, in this field, are there other major issues that you want to address? What is really missing?
There is many issues in this work. First is the fact that you need to fix the length of your signal, so you need to know what type of patterns you're looking for in the signal. This is a hard issue. So for physiological signal, where you look at it, you see kind of what is the scale of the atoms. It's easy, but if you go back to this kind of signal, here, if you don't have a domain expertise about the fact that the brain response is roughly something that is lasting half a second, then it's very hard to calibrate this kind of thing. So I think this is a major issue. If we want to go to do scientific discovery with this kind of tools, it's not clear that we can do it with this kind of direct convolutional dictionary learning techniques. I think something that would make sense is actually maybe move away from this convolutional dictionary learning and use maybe some object detection like deep networks that are able to actually learn objects of various size, but just based on their similarity. And so this is the direction we are trying to move in, for instance. And there are also like how do you jointly model the distribution of events and the event together. I think is a second direction that I think is very, very interesting.
So now we're going to go through the next reviewer and last one. So Professor Romain Tamnar, and since we still have no microphone, so
I will repeat.
Thank you.
Okay, so my first question is probably related to the last one. Before I dive into questions, I wanted to thank you for inviting me in that jury and for the very nice document that you wrote and the very nice presentation that you gave today. That's very impressive, so thank you for that. And I can then my question. So on this topic, you have in your manuscript the perspective saying that you want to go towards less hyperparameter. I don't know if what you meant by that is what you just answered about moving to completely other kind of methods, or if you believe that in that range of methods you could make it better, and maybe it's related to what you presented today that was not in the manuscript. The thing on experience.
So one question. So the question of Romain was on the manuscript. I mentioned that one direction I want to move in is a direction where we have less hyperparameter for this kind of methods. And what is my take and what in which direction I think this will steer me. So I think the first I think a nice way to put it is how do you actually validate all these hyperparameter in an unsupervised technique, in an unsupervised way. I think this is like hyperparameter selection, unsupervised hyperparameter selection, and there is probably some ways to try to come up with nice way to say, okay, I capture actually the distribution of the signals. And so this is something that is done a lot, for instance, a domain adaptation where they're trying to match some statistics of the different domains, and they select hyperparameter based on the fact that they manage to map one domain to another. And I think this is something that could be used for this kind of unsupervised hyperparameter selection, let's say. Another direction is, as you mentioned, probably moving away from convolutional addiction learning and very parametric families, and maybe moving to some more like deeper architecture. The danger of this is if you go too big, at some point you lose a bit the possibility to go back to trying to understand what is happening in the signal, which is something that is maybe as important for when we work with medical doctors as the result actually. The result of the prediction is interesting. If you get some nice results, they are happy. But if you cannot explain to them why you get some nice results and what they can understand from the signal, and if they cannot relate with this, it's actually quite high hurdle to make your model go to clinical. So I think there is a trade-off between the two, and we need to think carefully about this.
Maybe another question on benchmark. I really love this idea of community benchmarks, etc. My question is, how can you deal with the fact that the foundation model that you might be interested in evaluating at some point, they tend to train on all the publicly available data?
Oh, this is a very hard question. So the question is, in BenchOpt, if you want, it's a good way. It's a good way to compare a method, but how do you deal with the fact that a lot of method tend to train on public data, and basically will overfit the evaluation that you are proposing. I have no magic trick to avoid this. I would say what I think is nice in BenchOpt is the fact that you split you split many of the method, of the data set, of the parameters of the evaluation into different files. So this means that you can keep some private files to reevaluate on private benchmark, let's say. You can also play with the parameters. The goal is to be able to play with the parameters of the input. You can do some processing. You can also change a bit the metric between the evaluation without retraining everything. And so I think having a nice organization allows us to have tools if we find some good ways to reevaluate model, to do it efficiently and easily based on the same infrastructure. So the goal of BenchOpt is not to solve directly this issue that maybe you're trained on the dataset that we are using, but to make it easy to add a new dataset to reevaluate everything. Because by design of the BenchOpt architecture, adding a dataset is adding one file. So it should be easy to rerun everything with a new dataset.
Maybe my last question, which is more philosophical question, is what do you contribute to open source? What's your motivation?
So the last question of Romain is, why do I contribute to open source? It's a hard question with many ramifications. I think I got infected by the virus during a scikit-learn sprint in 2015, in particular because of Gaël within in the room, because of Gaël, Alexandre, and Olivier. And I think I contribute to open source mainly because of two things. First, I think it's fun. And maintaining a project like JobLib, I love it because it's very complex, a lot of complex problems to solve, and usually you know that there is a finite time solution, unlike for research projects. So it's nice to have as a side project for research. It's a nice escape sometime. And the second thing is that I think also it's nice to be a team player and to say, okay, I'm doing something and we are building all our methods based on the software that is developed by many different people, and so it's nice to contribute to this stack. So I mean, personally, I appreciate being this, and it's rewarding, I think.
So now I propose to go through the other members of the committee. So I propose to begin with the American side. So with Professor David Dono. Can you hear us, David?
Yeah. Do you hear me?
Yes.
Yeah, I was the obnoxious guy asking questions during your talk. I'm sorry. And I also apologize for the behavior of our politicians. Yeah, I have lived in France, and it's just shameful what's going on on this side of the Atlantic. Okay, anyway, as a statistician, I should ask something about noise, but I think it's less important than to ask about what you have currently on the screen, bench opt. So first of all, as you know, but maybe the people in the audience don't, I have publicly applauded the work that you've done with bench opt. I think it's essential. So, however, I wasn't completely satisfied with your answer of why do open source. So I want to say that there is some difference between open source and reproducible computational science. I think in this era of computational science being ascendant, if we don't actually share code and data, then, we're just faking it in the sense that nobody really understands what we've done. Nobody really believes what we've reported. Nobody else can really benefit from anything we say. We're in this world where there really is only one way to have a cumulative scientific enterprise. I also think that if people at the PhD and junior faculty level are not sharing their code, they miss the biggest opportunity they'll ever have for impact. Because by sharing their code, they give a chance for other people to be influenced by the work they've done. If they don't share their code, other people cannot actually make use of it immediately. I know you know these things, so I'm not trying, but I feel you could have said those things. So that's just my little
So
speech.
maybe to answer this, I think bench-opt is not just open source. Let's say that I answered open source thinking about my work on open source like JobLib, scikit-learn, working on this all this community package. For me, bench-opt is there is three components. It's open source. It's true that you have a library that is open source, but it's also a community work to make people understand exactly what you're saying, that sharing code helps everyone and allows to build better tools to better evaluate progress. And so I think I agree, I completely agree with you, but this is more than just sharing code. It's also sharing practices and agreeing on the way to measure the progress. And it's actually something that is quite hard to do. For instance, I've tried for a long time to come up with a benchmark to evaluate optimal transport. And in Paris, we have three people that are very strong and very doing a very nice development in optimal transport. There is Marco Cuturi, Rémi Flammary, and Jean Feidy. And the three of them are doing some super nice code, open source, sharing them and everything. And so during a bench of sprint, I put them in the room saying, okay, we should have a benchmark to evaluate. And actually, so they stayed an hour in the same room. They talk to each other, but actually they don't agree at all on the way to evaluate the optimal transport. For very good reason, because they are not interested in the same in the same object or in the same result for optimal transport. And so this is a community effort of trying to come up with the right way to evaluate things. And I think this goes maybe beyond open source. And this is why I did not answer what you said. But I agree with you that sharing code is sharing code, and trying to come up with stuff that can be merged together is very, very important.
Right. Yeah, I would agree. Open source is necessary for reproducible computational science, but there's a whole other set of things required. On your some of the later slides, just to follow this one, let's see if we can find one. You had one that showed SGD solvers of ResNet. Oh, maybe this is it.
Yeah, this one.
Okay. So first of all, I wanted to say thank you, I guess. So you're saying that SGD data augmentation, momentum, and cosine LR, that combined recipe is something that emerged out of a combined study that's listed here. Is that right?
Yeah. So the thing was, what are the tools to reach the state of the art for this particular architecture on these different three different data sets in terms of test error and generalization error. And actually, if you just look at vanilla HDD, you get some very some decent performance, but are far away from state of the art, and you need a lot of extra trick. And so actually, you need both data augmentation, momentum, cosine learning rate scheduler, and weight decays to be able to reach the nice performances. And these performances are the ones that are considered as state of the art for ResNet 18 on CIFAR10. No one managed to reach better performances. So yeah, that was the goal. Yeah.
So the evidence supporting, so let's say the general prescription that's the downward pointing golden triangle sort of emerges from this benchmark comparison.
Yeah, so the legend here is not perfect. Is actually the upward pointing green triangle that is the best one, that is adding some weight decay. But it's exactly the one that emerges from this comparison, which was an ablation study. And actually, we were not completely convinced by this at first with Zachary, because here we are doing standard practices for deep learning optimization, meaning that we are optimizing and we are doing some early stopping on the test sets, which is the classical thing. So we replicated this study using separate validation sets to be able to do the early stopping, but we were actually able to obtain the similar performances using the same combination, and we had kind of the same ranking between the different methods. And so yes, this is what emerges. The nice thing is that maybe something that is not showing that much here is that there is actually another optimization method that is called look ahead. That was a recent paper that we were able to evaluate in this thing, and that was able to match actually the performances, but going a little bit faster at the beginning, but not really faster in the overall time. But I mean, once again, this is one benchmark. This is one way to benchmark. Maybe there are other stuff to add, but the thing that was quite important here is the fact that we explored a lot of combination to try to come up with the right way to optimize this kind of architectures.
Okay. So I think this sort of study is very important because clearly in empirical machine learning, there are thousands of papers a year, and to have some systematic way to make recommendations for these kinds of things, to have an evidence-based procedure for arriving at recommendations and so on, I think this is, absolutely essential. And I think I've benefited from it, so that these things actually somehow get spread out, and even people who are just consumers of ResNet 18 training benefit from them. So yeah, thank you for that. Okay, I've asked a lot of questions, but I'll just go back. I think slide 3 out of 37 we could just look at for a minute.
3?
Yeah, here we go. Okay, on this one, just as I'm a statistics professor, statistics PhD, so I have to ask, look, we don't believe we don't believe that effect precedes cause. And I guess on this plot, the vertical dashed green line is the moment of the stimulus. So
Yes.
the distance of wiggles prior to that is simply an indication of the noise in the fitting procedure that you're using, in my opinion. Would you agree or not?
Yes. So here actually, the picture is not. I see. I simplified a lot the picture, because to obtain this kind of effects, we are using some pre-processing. We are using also some baseline, some normalization before the stimulus, and so everything that is happening before is indeed something that should be considered as noise. So it's resulting from noise. The fact that,
Noise or processing artifacts.
yeah, or processing artifact.
Okay, so
So
then good.
here
Okay,
you,
so
you see that you have some oscillations that are processing artifacts, because you have still some residual oscillations here that are probably due to a different kind of noise.
right. Okay. So after the dash, so if we just look at the vertical size of that, maybe it's, the typical vertical oscillation is maybe 40 units, 30 units in this area
Yeah.
before the green line. So that's sort of an index of the noise and processing artifacts in your procedure. So obviously what's happening around 0.1 seconds is signal is way bigger than noise. But a lot of the rest of the time, the signal is not so much bigger than noise, it looks to me.
Yeah, so the response is really this thing that is located around 0.1 second. The rest is mostly noise still.
Right.
So
So,
I agree that here basically the response is mostly this butterfly that you can see here, where you have like really like big amplitude that is not cancelled by the averaging, and this is what is believed is the brain response, and this is something that we kind of recover using all the dictionary learning later on. That we have some effect around 100 milliseconds after the stimulus.
okay, and the actual thing I'm looking at here is a kind of a mean across magnetometers. Is that right? And then you're
It's a
showing me
mean.
102 different
It's a mean.
means.
It's a mean across windows that are centered along the stimulus.
Mhm.
So you take multiple windows, you average each channel by itself, and here the color is actually which channel you are averaging here. Here you have the color encode the location of the channel actually. And here you
Okay,
averaging actually 55 stimulus. So it's not huge, but it's something that is like classical in electrophysiology, text-based electrophysiology recordings.
Okay, so you showed us, I think, a general model that allowed for K of these bilinear components to be present, but I'm guessing here we're just looking at one of those components.
Yeah, so here this is the class. This is just the this one is just the classical technique that is just averaging along the stimulus. What you can do is, if you use dictionary learning, you can learn multiple components, and this is what I showed here. And here, these are exactly the same, but you only learn one temporal component, and the spatial mapping of this, we have a special structure for this kind of process that helps us to get rid of more noise and to have a better response actually with this kind of signals.
Right. Okay. So when you say it's helping you get rid of more noise, so how would you, like, what is the evidence based
So the
for that
evidence is
claim?
actually you have some parts of the noise that is independent for each of the sensor, and so as you're using a single temporal atom, temporal atom for all the sensors, you have some averaging effect that kills a little bit more noise than if you do the averaging on each of the channel. So basically here, this temporal response that we recover is a temporal response that is average across the repetition of the stimulus, so of the auditory stimulus. So we have 55 auditory stimulus. So we average across this 55 repetition, and we also have some kind of averaging effect because we look at the single temporal component for all the spatial components. So this is something probably we could also maybe enforce manually, but it would require a little bit of work. Here, it's something that is embedded in the model.
So you're showing here atom 2 and atom 6. How many total atoms in your decomposition?
So I think in this composition we were using 20 atoms, and so the atom 0 and 1 were the atoms that encode actually a strong artifact that we can find in the signal. So you have a lot of artifacts that come from heartbeat or eye blinks, and the others actually you have also other type of artifacts, and you have also some less typical atoms. Here, this is some kind of representative atom that are the one that are interesting us in this case, but it's not all the atoms. It's also, I think, these two atoms were selected with an automated procedure that was looking at the atoms that were the most correlated with the auditory and visual stimulus, because we were looking for this kind of responses.
So when you picked 20 atoms, was there some criterion that you're using to decide that 20 is a good number?
This is a very good question. So what we do is actually usually we start with a few atoms and then we increase the number of atoms. And the nice thing about dictionary learning is that when you increase the number of atoms, once you can always increase, and at some point all the atoms will never be used. Actually, the sparse activation will be always 0. And this kind of give you a hint of how to select what is the right number of atoms. So this number of atoms is not something that is really complicated to set in this context of dictionary learning where you're looking for patterns. The complicated hyperparameter to set, which is set mostly by hand, is actually this lambda parameter. You have some ways to try to guess what is the right parameter, but for now there is no clear evidence on what should be the right way to set this parameter.
I have some thoughts, but maybe we should talk after your party someday. I have no more questions at the moment.
Thank you very much.
Okay, so thank you, David. So I guess I should apologize not to have precise the rules of this French degree at the beginning about the question session, I mean. So now we're gonna have Patricia Renaud-Bourret, who is a senior researcher at CNRS. So Patricia, can you hear us?
Yes, I'm here.
Amazing.
Okay, so first of all, Thomas, I wanted to congratulate you for very, very nice work, very broad. I'm also very happy about the reproducibility part, because, you know, I'm also working a lot in neuroscience, and reproducibility is a big issue. Like 60% of the papers are not reproducible, and this is due to various stuff, but one of the stuffs are what you are trying to fight against. So really thank you for doing that. So I have some questions, a bit in line with what David said, because I'm also a statistician. So about the choice of K, again, if I'm, I don't know exactly what are the results you proved, but I think the fact at one point you stop adding noise is also adding real atoms in your dictionary, comes from the fact that you don't find anything that is above a kind of threshold which should represent like the noise level and should be linked to lambda. And if you change lambda, probably you are not going to have the same number of atoms in your dictionary that you would like to put. Am I okay, or am I
This
missing?
is completely right. This is exactly what is happening. Basically, you choose the level to which you cut the number of atoms based on lambda. So this means that setting lambda is actually, I mean, you can find a procedure that allows you to select K once you have fixed lambda. But then the question remains, how do you select lambda? And as I said, there is no clear procedure for that. This is what we were also mentioning a bit earlier with the question of Romain on how to set this hyperparameter. I think something that we are moving more and more toward is actually to use statistics and to say, okay, maybe the nice way to measure if we fit well the distribution of the distribution of the signal is to keep some part of the signal on which we don't learn, we don't set this lambda and k, and then look at how well we reconstruct this signal, and or maybe some downstream task that allows you to to evaluate was this the right choice for the hyperparameter. This is something that we are looking at, in particular in the case of anomaly detection, for instance, trying to see if you learn from some signal, some kind of model that is this convolutional dictionary learning, the parts that you don't reconstruct well, if you have like a nice statistical stationarity in your signal, the part that you don't reconstruct well are probably the parts that are that have different distributions that might be anomalous. And so this is something that we are looking at. And in this sense, we might have a downstream task that allows to select lambda. But it's hard to say we can select lambda without having some clear downstream task, I think.
Okay, thank you. I had another question because I think it's on slide 23, if you can go there. Yes, yes, perfect. Here there are various things that I'm wondering. First, it's when you go from empirical data to events, I think it depends on the events, but maybe you cannot overlap them. And is it something that you take into account when you are minimizing the whole stuff? I mean, maybe like for heart beats, it's very hard to have like two shapes of heartbeats that are superposing because it's something really weird for the heart. Whereas maybe for EEG, it makes more sense to have overlaps between shapes. And I'm wondering if you are using that or not,
So
depending on the problem.
It's actually an excellent question, and this is some thing that we did not do yet. So we did some recent work with Charles Truong on actually if the atoms don't overlap, you can solve some this kind of problem in a very efficient way, and exactly with instead of using the L1 norm to penalize your sparsity, you can have a L0 norm, and you have the exact algorithm that is very efficient. And so here we did not use it yet for this kind of problem, but I think in this case it would make a lot of sense. That being said, indeed, for EEG, you have some atoms that might be overlapping. It's harder to say that the atoms are all separated, but I think it's worth actually trying to evaluate both cases together, and we should move on also with this kind of ideas. So I mean, it's a very valid question actually.
Okay. And the other thing I was wondering if when you look at the picture in the middle, in fact you recover atoms, but you have also a height for each of those atoms. And it seems that after that you just discard this information and you don't really take it into account. And I was wondering if there is, depending on the problem again, some information in the height of those atoms, and that people might use, for instance, when you are looking at earthquakes data and Hawkes processes, the magnitude of the earthquakes is something that you can also try to model, like how magnitudes impacts further stuff in the process. So are you thinking that?
Yes, so that is an excellent question. That actually in the original model that we did with Fadin, we did not took into account the mark. So it's a mark point process where you can take into account the magnitude, and we did not take into account this thing. But in the later, in this later work that we did with Virginie Loison and Guillaume Serman, we actually extended the Fadin algorithm to be able to work with mark data, and to be able to work both with the fact that you're trying to predict the mark, and you also trying to and the mark is also has an influence in the later thing. So this is something that you can actually that is represented here, where you see that the smaller the event, the smaller is the intensity change.
Okay.
So we tried to do this. It's actually working pretty well, and it makes sense in the context of a noisy event detection. If you consider that this thing corresponds to the confidence in the detection of the event.
Okay.
And this is something often, like most of the event detection things allows you to have like some kind of probability that this timing is actually an event. And so using this, we can use it. And for CDL, this is the 8th of the activation vector. Yes.
Okay. I had a final question, which is a bit provocative, because I'm sure your method in general is okay, but I was really thinking about the neuroscience experiment that you were showing with the auditory signal and visual, the auditory ERP and the visual ERP that you want to recover. Yeah. So in fact, for this thing, if I'm not mistaken, you have like 3 process that you want to see their interaction, maybe, which is like the stimulus, the atom 2 and atom 6. And in fact, the way you want to guess, well, the intensity, I think what later is just interaction between, say, atom 2 and the stimulus, atom 6 and the stimulus, but not really atom 2 and atom 6 together. And if you are just looking at the link with the stimulus, then your likelihood, there is not a real sum over all the previous points. It's just the one stimulus that is just before. And so you don't really need to have those fancy stuff to compute the log likelihood or the least square. Am I right, or am I misinterpreting something?
You are totally right.
Okay.
So here, indeed, in this case, you have only the stimulus, but actually, you only care about the effect of the stimulus on the activation of the later pattern. And so, if you choose well your parameter, you have something that is very easy to compute. But the interest that we had is okay, can we make actually this method broad enough to be able to handle many different situations, like the situation where you have auto excitation, for instance, with this kind of patterns, with ECG, for instance, but also something that we were quite interested when we developed this method is also to see about the induced response. So in neuroscience, once you have a stimulus, you have the evoked response that is the strongest response that you have in the brain, and you can have also some kind of induced response that is happening a bit later on in the brain. That is something that happened after the stimulus that is known, but it's not known what is its shapes and what is all these delays work. And we were interested when we started this work to try to quantify actually, once we have this, can we actually see another activation later on that is related to the stimulus? That is related to the stimulus or related to this to this event, and this idea actually phase lock on this event. And so this was the question that we had for this.
And did you find any like post signals that were more hard to detect that you could have with your method?
So for the neuroscience thing, no, because we had some issue with scaling enough the event detection part. So we are not there completely yet. So we were not able to investigate the second part where you have the induced response. For the ECG part, the method was quite important because actually when you have a lot of noisy events, to be able to apply an app, you need to do a lot of different inference with the noisy events. And in this case, you don't have this nice separation between the events. So here we really need this method that is a bit fancier.
Okay. Okay, and one last question, which is a bit more philosophical and from the neuroscience point of view. Sometimes in neuroscience, what is also super important, at least in the interpretation that I've seen, are the rhythm of the various like alpha, beta, theta, and stuff like that. And the way you are imagining what is the EEG signal, you completely erase what those rhythms would mean. And do we have to choose in between the representation with atoms and the representation with rhythm, depending on the question? Or would you think there is a way to reconcile both point of views?
So that's, I think, an excellent question. I think so. My understanding of neuroscience is not super large, but it comes a lot with discussion with Alexandre Grandfort. And there are several papers showing that there is some kind of Fourier fallacy, where you see that there is some brain rhythm that are considered independent, which usually are not always independent because you have a lot of harmonics that are also happening. And when we started working on convolutional dictionary learning for this kind of models, it was to try to see if there is some pure rhythm, or if we were able to find some atoms where you have components that are both in the alpha and beta, for instance, together, and that are actually linked together. And so what I think is this Fourier analysis, the frequency-based analysis representation of the signal is very convenient, very important. But I think that this thing, in many cases, this rhythm arises from the fact that you have multiple times the same patterns happening. And in particular, we were interested when we started this work to try to find the new waves that are happening after some somatosensory stimulation in a neuroscience perspective, where these new waves are actually some oscillation in alpha that have some harmonics, that some clear harmonics in beta band, and we are trying to kind of show that these harmonics, the fact that you consider alpha and beta band in this case doesn't make sense. So I think the rhythm kind of explain what is the frequency at which these patterns occur, and so this representation makes a lot of sense. Still makes a lot of sense, but I think if we, in some cases, this rhythm come with some patterns, and having access to the shape of these patterns allows to avoid thinking that the frequency are actually are actually independent, because actually they arise, these two frequency arise from a single effect. Don't know if it's very clear, but
yeah, yes, very. Okay, so thank you. I'm done with my question. Thanks a lot.
So I guess it's my turn. Maybe I can stay here and ask you a couple of questions.
I will repeat the question from Edouard.
Okay, I really did enjoy like your presentation. Actually, the whole landscape, like with chapters, like maybe someone having a background in signal processing and working a bit now on optimization. So really, I did enjoy it a lot, and you had a really great focus on benchmarks at the end. That's also very cool. So I'm going to just begin with some very nice questions about like the chapter 1. So I'm just wondering, so when you're working with this rank 1 convolutional dictionary learning, so CDL, pardon, I think there was this time a plethora of words coming from the computer visions, like about trying to work with those dictionary learning with patches, these kind of things. And I was wondering, in this context, like, were there some papers which were related to your approach? And I had something in mind. One paper called Convolutional Dictionary Learning via Processing by Elad et al. And I was wondering, how do you relate to them, these kind of things? Maybe you try to benchmark them?
Yes, so maybe there is. So we benchmarked a lot against. So maybe let me repeat the question. So about the chapter 1 in my manuscript, where I worked with convolutional dictionary learning. Around the same time we were working on this kind of work, there was some concurrent work by a team from Mickey Elad and others on computer vision using this kind of idea of convolutional dictionary learning and these kind of things. Do we benchmark against it, and how do we place ourselves compared to this? I think it's a tough question, but no. So I think from an optimization perspective, what they did was mostly using ADMM. We were advocating for a coordinate-based algorithm, so coordinate-based algorithm, and we benchmarked a lot against these different optimization strategies. In particular, there is actually a library implementing a lot of tools which is called Sportco, and we always compare all the algorithms that we did with Sportco, which is kind of the other reference library that exists. And usually we are faster for the use case that we have, where we are looking for very sparse signals. They usually are in the regime which is with a much lower sparsity, where using ADMM makes more sense. And so the thing is, it's not so easy to compare this both this method, because the purpose were quite different. Usually we were working on simply finding patterns, which is a very different topic than what they are doing using denoising in images or some deconvolution, or so working on images. But recently we started working on this kind of topics using like dictionary learning to do some plug and play methods, for instance, in joint work with Audrey Repetti, Benoît Malézieux, Mathieu Kowalski, where we try to bridge a bit between the two, and where we see that there is some actually quite nice link between the two. But depending on the application, I think both work were quite interesting actually.
I see that. And if I make like push and push up, do you think one way to understand like their method is that so if you are doing some randomized selection of the atoms in the coordinate descent scheme compared to right now what you're doing is taking like selecting like the one which activating which is the maximum, like doing something randomized versus maximum, like one way to get from one to the other. Maybe I'm too specific. I'm really thinking about like the paper of Elad.
So the paper of Elad, they are using ADMM, no?
Yeah, yeah.
But ADMM is a global method where you update all the coordinates at once, whereas we try to update only a few coordinates at once, let's say. And so I think the approach is very different because if you use coordinate descent, usually you start from 0 and you add some coordinates, and so you have something that is very sparse in the end. So if you look for something that is very sparse, it's quite fast because you're not too far away. While the other way around, as they look for something that is more dense, they are using ADMM, and ADMM is something that produces some estimates that is more something that goes from dense and that is sparsified as you go. And so as they look for something that is denser, it makes sense. And so really like it's more like basically you can go from one spectrum to the other by selecting the number of coordinates that you update at the same time, I think.
I've got like a second question, like when it's a specific question, so like the size of the supports that you are using with the way you are trying to characterize the event distribution with point processes. So at some point you have like a W parameter. And I was wondering like if this was linked to the approximation quality in this case, like if the W related to it or not. I was a bit surprised when I checked there are some proposition in your manuscript and there was no link with that, and I was slightly surprised.
So when we consider here the way we go from the event to the aux parameter, we need to fix the support of the kernel, and the question was is it actually related with this thing that we show here that the bias due to discretization goes to 0. Actually, the bias due to discretization goes from the fact that we go from continuous time to discrete time. So we project the time on the grid. And so we need some regular grid, and so we need some delta is the time, the inter-event time. So it's not related to W. W is related to the length of the support of the kernel. And so basically it's the maximum time for which you think that an event can have an effect. And this is actually something that is very important to make some efficient computations because this allows you to reduce really the window on which you look at other event. And this we did not discuss too much in the different work that we did, because we think that most of the time you kind of have an idea of how long you have this kind of. But this is true that it can be an issue. There are several ways. So you can take a very long window, but if you take a very long window, then the efficiency can drop. Some other work consider using some recurrent neural network to try to encode some infinite context lengths. This might be a good way to avoid this kind of thing, but then you lose also this interpretability that we were thinking about before. So it's like really, but for now we don't have a clear way of how to set this parameter in a sound way, except the fact that in the case of ECG, for instance, you consider that it might have an effect on 1 or 2 Earth bits, but not on very large number of Earth bits.
Now I have one question about like chapter 2. So okay, so you're familiar with this guy, and I was wondering, so being like someone from like having a background in Ukraine, so I was wondering the reason this guy exists is because it's either for like the first iterations of the scheme. So basically, you want to solve something like FISTA much faster,
in like 10 iterations compared to 100 and kind of things. And in your last lecture, mainly you discussed some asymptotic results. And I was wondering, like, if there is kind of, if you had like some insights on how to figure out which one should work. So I guess learning helps, but maybe you have some comments on that.
So the question is about the Lista architecture and the fact that in many of the work that we did, we consider asymptotic performances of Lista, while usually in practice, when you want to use the Lista, you want to have something with only very few iterations. And so the thing is, the thing that we were interested in is actually, like, a lot of work that we did on unrolling was to say many people are using unrolling as a way to say, okay, I'm having a layer that is interpretable as the solution of an optimization problem. If you want this to be true, then your solution needs to converge when you have asymptotic rate, or you need to have some good link with this. And if you use very few iterations, actually you lose completely this interpretation. It's a very nice architecture, but you cannot say, okay, I'm safe because I'm solving the original problem. And so what we wanted to know is what can we do to reconcile a bit this? What is it possible to learn? What is not possible to learn, and how do you match between the two? And so basically, this was the idea of this work. So this is why I think this slide is actually what I really think about unrolling. I think unrolling is a very convenient way to design some nice architecture that have some properties like sparsifying or stuff like this, that are stable because by its construction, your iterative scheme is stable. If you choose your step size or stuff like this that are well, but it's not something that should be interpreted as I'm solving an optimization problem. And this link is broken, and there is a trend of papers saying, yeah, when we are using Lista, we are very safe because we are solving Ista with a linear convergence. This is not true. And this was a bit what we were trying to probe with this line of work. In particular, with CDL and non-smooth things, we see that even the gradient is not a good estimate of the gradient, or for a very few number of iterations, but it's improving so little that it does not really worth doing all the backpropagation. Just take alternate minimization.
So now for the chapter 3. So I really like benchtop. It's very cool work. And I was wondering, like, to me it seems, and maybe this has changed, but like it seems to be a bit like coupled to say some batch optimization problems, which means that that's some problems where you have some optimization which is structure. You have a fixed data set. You have like a definite like number of iterations that you allow yourself to apply. And so I was wondering, like, if you plan to extend that to things like, I'm just randomly saying, like online learning, meta learning, reinforcement, these kind of things, and how you envision these kind of things.
So the question is about benchtop and the fact that it's very tightly linked with optimization problems, basically. So this is true because, I mean, the DNA of benchtops is from people doing optimization saying there is not enough benchmark in optimization. So we started with this problem. We have this discussion many times already with Gail, so I have a clear answer for this. I see him smiling in the audience. So this is. But the thing is, we are moving away from this because actually, the root of benchtop is a way to organize a data science, a machine learning problem, where you separate the data, the method, and the evaluation. And then you just want to have a clear way to define what are the parameters that you can vary. And you want to have a pipeline that allows you to do a cross product between the different data sets, the different methods, and the different evaluations. And so this is the root of benchtop. And basically, we moved a bit away from this thing that is all for optimization. We are trying to have a separate template to create a benchmark for machine learning, where you don't have you don't evaluate for a different number of evaluation. You are just you can do whatever you want in your method. You just send back something that we can evaluate, that can be wrapped around something other. And so this is typically what we did for domain adaptation with the SCADA bench that I was mentioning at the end. This is for unsupervised domain adaptation. Here, with this benchmark, we have something where the benchmark, the dataset are multiple domains to one domain to train, one domain to target. In the methods, we are training the method using some cross-validation scheme to select the hyperparameter, and then we are sending back to evaluate. And there is no link to directly optimization per se, because we are just evaluating each method once. So you can do whatever you want inside.
Which means that you could work out with, say, a surrogate loss instead of things.
You can work with whatever you want. Then we just evaluate on the test set basically at the end. So you work with whatever you want, and we don't try to stop the optimization at some point with clever, fancy trick that are cool for optimization work, but that are actually bothersome for machine learning. We try to actually separate these two things in a better way.
So, and in your like efforts to integrate some, determining benchmarks and sort of things. I was wondering, like, so first, are you familiar with this paper of Benjamin Resch called "Do ImageNet Classifier Generalize Well to ImageNet"? Yeah. So basically, what they do is that they apply your permutations of like some vision benchmarks, and suddenly, like, the order of all the algorithm is completely swapped. And so I was wondering, like, did you have similar findings, or would you say that the cooking recipe of the ResNet 18 used by practitioners is optimal? Basically, are different people, some very good at tuning?
So the nice thing with this result is that they are reproducible across 3 datasets, 3 small-scale datasets. The goal was to go beyond that. The issue with this benchmark is that we tried to go with both TensorFlow and PyTorch. So the code is actually a nightmare to navigate because we had many different tricks to try to make them fit in the right way and everything. So what we need to do, and we did not add time the time to do it yet, is to try to make this benchmark again only in, let's say, in PyTorch, and incorporate more data sets. For instance, something that we really wanted to do at the end of this, but we never had the time to do it, is add ImageNet. Add an ImageNet thing and see does it work well or not. Because most people know that Adam is usually performing better than HDD. But is it with all these tricks or not? And this is something that would be super interesting. And it should be something like adding one data set and seeing if it works well. It's more complex than that because of the scale of the problems, of course. But we are working. For instance, using Slurm to kind of distribute all the training on big GPU clusters. So this is something that should be doable. We just need some workforce to do it. That's always the issue. Basically, we did a lot of different sprints with like more than 40 people helping on the benchmark and everything. It works super well for 3 days. We advance, we make a lot of benchmarks. But then the people that keep contributing to open source there are only a few. And so this is always hard to find the right balance because everyone is busy with other stuff. So finding the time to do some nice benchmark is something that takes time. This is why we should do it as a community effort. This is also why it's very nice to do it during sprint, because everyone like get some time for 3 days, and you can really advance and make some progress. And I think this is something that is quite important. All right, thank you very much. So I think now we need to move out of the room during the deliberation of the jury, and that's it. So I think the easiest is that you stay on this Zoom link and that you take some. I can leave my computer, and you can stay on the Zoom link, and I think you can. Oh yeah, I should turn off YouTube. That's a very good